Right.
If I remember right.
Mm-hmm.
Does that answer your question?
Right, yeah, it does, it does. Okay, so, and I know there was an explanation here that this motion observed could have been just due to deformation of the soliton and the way that the soliton position was being measured. But at the same time, it seems they went from 0 to a different velocity. And my thinking was that it wasn't the linear G gradient that caused the magnitude of the G gradient did, but it was the transition from no G gradient to a G gradient. That was what caused the acceleration. And then the resulting velocity was a factor of the magnitude of that G gradient.
Michael, are we supposed to be seeing something on the screen? I've got a blank screen in front of me.
Really?
The people on the right.
Yeah, it's blank.
Okay, I'm sorry. Yeah, I was actually displaying the. I was on my share screen. I thought I was displaying the paper here. Let me see.
Take it off and put it back on again.
Well, it could be that I have the presentation going and that's blocking. You don't even see the presentation, do you?
No, I don't.
Okay. Well, let me.
Well, I see something behind. There's something behind the screen. At the bottom, I can see a bit of the presentation from behind the screen. A little bit of it.
Okay. Okay. Let me just stop sharing and reshare real quick.
Right, and then share again.
Yeah. Yeah, that would have been very confusing. Okay, I'm just going to actually share this here. Okay, this is what I was showing.
Okay, we're seeing it.
Yeah, this is the Model G paper. Stationary dissipative solitons in Model G, and this is section 4.3, where the 1D particle soliton was modeled in a gravitational gradient. And it went from 0 particle velocity to different velocities depending on the magnitude of that linear G gradient, as I interpret it here. And then you can see, zoom in, there's a portion here where they go from 0 to, and then overshoot a particular velocity and then dampen back down to a constant velocity after that point. So it could be a measurement phenomena, but essentially it just suggested to me that nonlinear effects could produce an acceleration, and being that this was a test of a linear gradient, that it may not have produced the acceleration, the potential for acceleration that existed.
My view on acceleration is that it's due to the gradient affecting the particle's space structure, causing it destabilizing the structure, and the particle then jumps to recreate itself in a more symmetrical fashion. And when it does that, it accelerates. And that's why there's inertia, because it has to completely destroy its form and recreate it in the new reference frame.
Yeah, and could you repeat, what was it that caused it to?
Well, it's sort of like you having to move from one house into another. You have to pack up everything and move. And that takes a lot of time and energy. I think that's the same way the particle accelerates, that it has to destroy itself and recreate itself at the same time, so to speak. In other words, it migrates to a new shape that's moving relative to where it was.
Well, and that's what was seen here to some degree. Is that right? It did distort and then move. Is that correct?
In the experiment with Matt, what Matt did, we didn't see it accelerate. I mean, as it was moving, it was just moving at constant velocity. So I don't consider that the onset, I don't consider that an acceleration. That's just the beginning of the experiment.
Okay. All right. Well, that there could be the case, although it just suggested to me that that could be a possibility, that something nonlinear could produce an accelerative effect. And so I thought it would be worth taking another look at. So that's where I was coming from there, and I believe I understand your view too, but let me but that's where I was coming from. I'm going to go ahead and just cover the other bases for the hypotheses here. Can you see the slide screen?
No, not at the moment. We just see the paper. Yeah, I mean, you may have to go back to the original and then come back again.
Okay, I could do that. It's not that difficult. I'll just jump into it. So we should be able to see the slide screen here now. Got it?
Yeah, got it.
Okay.
Yeah.
So now, if a nonlinear gradient could potentially cause a soliton to accelerate, well then, where could we find some nonlinear gradients in the soliton model? And well, those could be the tails. Now, the tails, they're cyclic, they're nonlinear, and they're composed of x, y, and g gradients. It was the g gradient that was tested out that we were just looking at before that caused a velocity in the solitons. So we got all three of those components in the tails. Sure, they might be very minute, but it could be, but gravity is also a very weak force. And so but there may be an immeasurable effect. And maybe for larger particles, the tails could be additive. So all the particles might superimpose their tails on each other and create larger tails, which might actually have more of an effect. But that's a different deal. So, but they have gradients that are nonlinear and cyclic, and they have the potential to interact with each other. And then also, being that the solitons are radial, you would expect any interaction, most likely to be, any acceleration, most likely to be radial also, just due to their geometry. So that would lend itself to gravitational acceleration. And also, being that the tails are relatively uniform, that would also match with what we observe as a more or less constant acceleration of gravity, gravitational constant. So these are some of the things that I was considering that might support looking into the possibility of these solitons interacting via their tails. And then trying to move to the next slide right now. Yeah.
So that's something we could try.
Okay. Yeah. Yeah. So this is the idea I had, and I would consider it a low-hanging fruit because it essentially was almost done before with Matt Pulver. Just the conditions weren't in this exact scenario, but it's two solitons have already been seeded before, so we know that can be done in ETB stepper. The only difference is they just need to give them enough distance apart from each other to where it's just their distal, the extended tails are interacting and having a relative velocity between the two. So that way the tails can experience interaction between the other gradients from the other tail. So they'll see an increase in a G gradient, and then they'll see a decrease in G gradient, and so on due to their relative motions. And then if that works, it would be, I think maybe one interesting approach is to model it so that instead of having these particles just accelerating towards each other or going away from each other, is to see if we could just have the simulation ran to where they're essentially static relative to each other. They're in orbit. And I think that would make for an easy way to control that experiment without having these solitons moving all over the place. where they would be essentially be the same distance away from each other all the time. So we run the simulation and they're starting to get further away from each other. So then we tweak the parameters, and then they start to accelerate towards each other, and we tweak the parameters until they're orbiting each other. And then, you know, you've got a constant acceleration.
So you're doing this in 2 dimensions, huh?
That's a good question. Matt Pulver, he did it in 1 dimension.
Yeah.
Yeah.
It won't work in if you do it in 1 dimension and do the symmetry thing that Matt did. I don't think you can show orbital motion that way.
Okay. So yeah, that's something that we definitely would have to work out. Is it 2 dimensions suitable? Of course, 3D would be ideal, but then how much computation time will it take? Yeah.
Yeah, I did 3D and it took 30 hours. The models you have seen there have posted on Facebook.
Yeah. So, well, I mean, that may also be, maybe it'll just jump right into 3D. It all depends on how much time it's going to take for us to.
And which software were you going to use for this? Mathematica or what?
Well, I mean, I'm up for anything, but I believe, didn't Matt Pulver, he used ETD stepper for that, is that right? Or did he? I don't know. I just
He used Mathematica.
Okay. All right.
The ETD stepper was used to model the in what is it, in 2 dimensions, the to actually model it, but the Mathematica, from what I understand, was used to calculate to show the X, Y, Z, G concentrations in a 1-dimensional plot in 1, 2, and 3D.
Okay. And I don't know if there's any. Yeah, so that would be something that we'd have to work out for sure. So if it's in Mathematica, I'm not sure how difficult that would be compared to doing an ETD stepper, because I haven't done that approach myself. So,
Yeah, I can do it if I get the initial conditions. Import a relative velocity seems difficult. I don't know how to do that, except if you can do it with some kind of concentration configuration.
Well, do you think maybe it's possible to have an initial velocity on the seed itself? And
yeah,
then,
maybe, but the seeding is like the stationary 1 frame. So, and I don't see. You just calculate the next frame from the previous. So there is like no time. I can't see how you can get speed into that. Yeah, then I guess we had to redesign the system. Like giving 2 initial frames after each other as an initial condition, with a difference in location on both. That could be equivalent to velocity. But this is not how the system is programmed right now. You just give 1 frame as an issue.
okay. Well, so the simulation that Matt ran with the in 1D with the soliton with the G gradient, he was measuring all the different locations, the zeros of the soliton and so forth. That was all in Mathematica. So
Did he do velocity and acceleration in that model?
yes. That was the graph we saw earlier.
Okay.
In the paper. I can switch back.
Maybe there is some support in it in EDT stepper, but I haven't checked that far.
Yeah. Let me see if I can switch back real fast to that. Yes. That's a plot of time versus
Particle velocity. Yeah, you're right.
Yeah. So
okay.
And then,
Now,
I'm not
I
sure
see
how,
it's declining there a bit in the beginning, huh? Is that what you're referring to as acceleration?
well,
Here where it
zoom.
declines in the beginning?
Well, actually, it declines, yes. Because, okay, let's take a look at this blue one. Now, and the colors are hard to make out, but you see another blue dot here, and then possibly another blue dot here, another blue dot here. So that's the way I'm reading it. It's going from 0, and this is shooting all the way up to over 20 something, and then declining to a constant velocity. Same thing with this red one.
Yeah, it was the constant part that made me think there was no acceleration. I wasn't looking at this decline part.
Yeah, this is what interested me here. Yeah, because they look like they all start out from 0. There's a green dot, purple dot, purple dot, purple dot. And then there's one that just has a constant velocity of 0 here. So that was the one with no G gradient at all. Yeah. So, and then another part in the paper that, let's see, talking about seeding 2 different particles is it was discussed here a little bit, and this section here. Multi-particle states in 1D, and here's the double Gaussian seed fluctuation that was used to achieve that. So I don't know if these were all done in ETD stepper or some of it was done in Mathematica. I don't know. But
the plots with the kind of like Gaussian soliton, that's where we've got the x, y, and g. This one here. Can you see this one here?
yeah.
X, G, and Y. That's done in Mathematica.
Okay.
Those ones.
All right. So let's see. So we may have to do it in Mathematica. It's possible then. So, but being that it's been done before, it just seems like that would be the path. At least the low-hanging fruit is something that we could just repeat by just tweaking the environment just a little bit, the parameters, and possibly getting some really interesting results. Let's see. So I'm going to go reshare my presentation screen, and I'm going to wrap it on up. Let's see here. Oops. Yeah, where'd it go? Okay. So the only other thing I was going to add to the experiment proposal was then, if we are able to achieve acceleration or even orbital motion, then that would be conducive to then matching to the real world, the gravitational constant, and that might actually be able to be used to refine the soliton model itself, because that would be information that would be incorporated into the soliton that wasn't there before. And it could make it for a better representation of an actual particle.
It's just given me a notification that the meeting will be closed in 10 minutes. So I'll just go onto Facebook. After that, I'll just go onto Facebook and make another meeting. It'll take about 2 or 3 minutes. And then you just click on the Facebook page and it will start the new meeting.
Okay. All right. So, but that concludes the presentation. We already went through some questions, but if there's anything else, any discussion, I'm open.
So how long will it take to do this, do you think? This simulation?
Good question.
And what platform would be used?
David, you might actually have a better idea.
Are we talking about ETD stepper now or the other model?
To do this experiment with the 2 particles attracting each other.
Well, I guess it would take 30 hours then if we can set some initial conditions.
You have the software, David?
Well, I imagine that we use ETD stepper.
That's something you have, right?
Yeah, that just took the Matt Palver software. It's I can run it anytime.
Okay, is that Mathematica or something else?
No, he wrote it in C++ and he used
Oh, yeah. Okay.
with some libraries. External.
Is that the program he wrote for the Starburst site, where there's a page where you can play with Model G?
Where it shows it in rings. It shows it in rings, expanding out rings, going outwards to produce more rings, a larger ring and a larger ring. It's like
I'm not sure. He did this in 2013 or 14.
I've got the. Do you want to unshare it, Michael? I'll just show the screen where I put it on Facebook.
Yeah, I'm going to stop sharing. I'm done with that.
Okay, so I'll just go to.
Do we go to Facebook now?
I'll just go to Facebook and see it. If it turns off, then I'll make another meeting and then we'll come back later. This.
Yeah.
Where's this?
So.
Okay, so just go to Facebook. It was under. Can you see that?
I can.
ETD stepper. So this was the C++ code here. Can you see it, everyone?
Yeah.
Oh, is it? Okay.
So just run it.
Yeah.
So this is what the,
Then he configured it for 2D.
code does.
Yeah, if we can use 2D, that would be much faster, supposedly several times.
But this one takes like could take a day or two to run to get the resultant video. But the other one, the Mathematica, I ran it on I've got through the UCL remote server. I ran it the other day. It takes about Mathematica program takes about 20 minutes to half an hour to run. It produces about half a gigabyte.
This is centrally symmetrical, so one dimensional run would be sufficient. And I got some software from him in 2014. I wonder if that one can still be used. We can check on this. I think that one is also on GitHub.
So
what do people
next week we'll have done the experiment, you think?
That'd be awesome.
Well, I need the initial setup here because I don't get how where it comes from and so on. So if someone put the initial conditions on Facebook or somewhere, I can use it.
You mean in terms of positions or velocities or?
Concentration and kinetic constants.
Any initial conditions like basic seed and initial speed.
David, what do you think of this? What I've done here by adapting the derivation of reaction diffusion. Did you see that post I put up?
Let me see it again then.
Where is it? It's down here. Can you see here where I've added a rotational term to the total diffusive flux?
I just have the Facebook page still on my screen.
Sorry?
I just see the Facebook page on my screen now.
All right. Okay. What I'll do is I'll take it. I'll stop sharing, and I'll go to share that. Where's it? Here it is. Can you see it now?
Yes.
Yeah. So I've added it in the blue highlight. I've added a term for rotational motion. So
Okay.
the dv by dr is the omega
Oh.
here, and then multiplied by delta r to get it into the velocity component, and then multiplied by the concentration, the ethron concentration. So you've
All
got
right.
a term for velocity, and then an angular term for angular.
So this is a term you would like to add to the one-dimensional simulation.
Yes, we could. So I was going to try. I was just writing this little report to sort of like
Yeah.
express my ideas more clearly. So
Yeah, the one thing that might need to be adjusted then is the step width in the iterations. And I'm not sure right now if it would need a change or not.
well, Paul, you've in your derivation, you've taken out these terms here. You've taken out the relative velocity, and ended up with this term up here. You've taken out. So you put it in there, and then you said later on down here you said you got there's the term you got there again, and you said we may assume v equals 0 and neglect the second term from any consideration. So you've taken that out, and then you're left with this term here, and that's identical to the term in the model G. dg by dt and dx by dt. So that's what I was looking at the moment. I was thinking, and I've got this idea from stop share. So I've got this idea from. Can you see that here? You see that? So
Yep.
I can
Facebook.
yeah. So let's go to this. See. So I've got this idea from, here's one showing vorticity and circulation in fluid dynamics introduction. And then here was my showing my ideas of how we could include rotation, because at the moment it's just diffusion, Brownian motion in as like hitting in straight lines in billiard balls. So this is the document I found. This is the video I found. Can you see that?
Yeah.
But this is the video that was an introduction to. So if I just go to here, can you see? He's defining fluid rotation, and here, so he's talking about at point O, it's traveling with a velocity, and then at